Diagnostic imaging, review, quality assurance. So the important thing with quality assurance is that we are trying to take radiographs that will be diagnosable for the veterinarian. They shouldn't have to be able to struggle to see the body parts or the conditions that's going on. The first one that we need to focus on, the first piece of quality assurance, is kilovoltage peak potential, or KVP. This is going to control the electron acceleration and how the beam penetrates through the animal's body. This is also going to be the major controller of contrast. Contrast is our blacks versus our whites, or how we see the differences between two areas, such as inside the organ and the organ wall and the other anatomy. So we always call KVP the quality. Next up is milliamperage, or MA. And this is only a piece of the next factor that we set on our machine, MAS. So MA is going to be the controlling of the electrical potential and volume, or basically how many electrons we send across. So this is written as MA, and this is going to be the primary controller of density. How black are our blacks? How white are our whites? Are we seeing a lot of gray, or are we seeing are we seeing a better quality of the image based on how many electrons we send across? So most clinics don't adjust MA. We're going to adjust MAS. And so what we have next is our seconds, which is the other portion of MAS. And the actual amount of time that the beam is penetrating through the animal. This is very much like our camera and our shutter speed. So typically what we're working with is a 15th, a 30th, and a 60th of a second. Bone is typically going to be at a 15th of a second, or if we take 1 divided by 5, it's 0.07. If we take tissues, that's going to be a 30th of a second, or 0.04. And then anticipated movement for things like the lung and the heart, or a wigglier animal, we are going to take a faster shot, a 1/60th or 0.02 seconds. The shorter the time setting that we have, the less exposure to radiation. But the shorter the exposure time, we also will have a lower quality image. Our patients don't always hold still, so in veterinary medicine, it's even more important to have a faster shot than, say, in human medicine, for example. So we have to take milliamperage per second. We have KVP and MAS are the two main settings that you're going to be logging in your radiograph. So milliamperage per second is going to be the calculation between exposure time and how many electrons we're sending across. So MA times the time factor in seconds, or basically fractions of a second, gives us MAS. And MAS is the quantity. So KVP, quality, MAS, quantity, or the mass of electrons that we send across. So we might have an MA of 200 and our seconds 0.04. So it's just a simple math calculation of 200 times 0.04, and that gives us 8 MAS. We also have to consider the densities of our patient. So thinking about what's black, and what's black is going to be air. What's white is typically going to be bone, and what is various shades of gray will be the various tissue and the fascia in our patient. Distances we consider here. Focal film distance is the entire distance from the head of the machine to the receiver, whether that be a plate or the receiver, which can either be film or it can be the computerized receiver. The SOD, the source object distance, is going to be the distance from the head of the machine to the patient, and the object film distance is going to be the distance from the patient to that sensor. So source object distance plus object film distance is going to equal focal film distance or source image distance. For density, this is the degreeness of blackness and whiteness on the film. How black are our blacks? How white are our whites? If we are seeing grays, we're going to need to adjust, especially in the background of our film. Mainly this is influenced by MAS, but KVP can have some contributions to it as well. If the density is too dark, we are overexposed, we've burnt our toast. If the density is too light, we are underexposed, we still have raw bread. And in addition, the time in the development for our films and the chemical temperature can have a big influence on density. For contrast, this is the difference between two areas of film. And one of the things to note is opacity. Opacity is like opaque or whiteout. So you're in a blizzard or in a snowstorm where you can't see out very far. So this would be no detail between the organs and the tissues. And so what we need to see is a difference between bone versus tissue. Bone will be white because it's less penetrable, and tissue will be darker because it is easier for the radiation to go through the tissue. SANTE'S rule is how we figure out the KVP settings. And SANTE'S rule is going to be 2 times the thickness in centimeters of the area to be radiographed. So whatever you measure with your calipers in centimeters, plus source image distance, which in a stationary machine will be 40 inches. So whatever the thickness of the patient is in centimeters, plus source image distance, which is a standard of 40. SANTE'S rule will work with our MA settings of 150 to 300, in other words, stationary machines. So SANTE'S rule example here is that we need to measure a dog's thigh for an x-ray of a femur. And so we get 10 centimeters. 10 centimeters times 2 gives us 20. So thickness times 2 plus the source image distance. So in this case, we would have 20 plus 40 and a KVP setting of 60. The radiographic density is the degree of blackness on the film, and it gets impacted mainly by MAS, lesser so by KVP. Good density is the image on the left, which you see the horse's limb, where we have whites versus blacks, and a little bit of grays in between. On the right-hand side, where it's very, very difficult to see, you have a gray background of what looks like maybe a pelvis. Poor density. The MAS or the KVP is too low in this situation. So MAS is the primary controller of density, and this is going to be that degree of blackness on the film. How many electrons we send across is going to have a major impact on how our results look. If the density is too dark, it's overexposed and we need to lighten it. If the density is too light, it's underexposed and we need to darken or add to our settings. You've seen this one before. This is if we have decreased density on the left, if we have increased density on the right. This can be caused by overexposure on the right-hand side, overdeveloping, chemicals are too hot, the screens are too fast or don't match. On the left, underexposure, where our films are too slow, don't match the films, underdeveloped, chemicals are too cold, or if we have old or exhausted chemicals. Usually what we have to do, if we have what looks like something on the right here, we need to decrease our settings. And you can see on the top one, our MAS is too high. On the bottom one, our KVP is too high. We adjust one or the other, but not both. If we need a major change, we are going to decrease our MAS. If we need a minor change, we will decrease our KVP. On the left, we have what is underexposed by MAS on the top. On the bottom, we have underexposed by KVP on the bottom. And so if we need to adjust either of these, if we need a big change, we'll change MAS. If we need a small change, we'll change KVP. And hopefully we can get to that image in the center. How to fix our KVP? If our original settings are 65 KVP and 1.5 MAS, if we make it only a 4 to 5% change, it's a barely noticeable difference and not worth a retake. So we need to increase it by 20% if it's too light. This will double the exposure. So 65 times 20% or 0.2 gives us 13. So 65 plus 13 gives us 78 KVP. How to fix if it's underexposed? So our new settings will be 78 KVP, 1.5 MAS. If on the other hand, it is overexposed, we're going to need to decrease it. And to change KVP, we decrease it by 16%. So 65 times 0.16 gives us 10.4. So we would say 65 minus, because we're decreasing, 10.4 gives us 54.6 kVp. So our new settings would be 55 kVp and 1.5 MAS. Keep in mind, every machine is a little different. We don't usually have fractions for kVp, so we usually round to the next closest number. If we need to adjust MAS, our original settings are 65 kVp and 1.5 MAS. If we change it 30%, it's a barely noticeable difference and not worth a retake. So instead, we need to change it 50%. To increase it, if it's underexposed and too light, we will take 1.5 times 50%, or 0.5, gives us 0.75. And we need to increase it, so 1.5 plus 0.75 gives us 2.25, and our new settings are 65 kVp and 2.25 MAS. On the other hand, if it is overexposed, we are going to decrease it by 50%. 1.5 times 50%, or 0.5, gives us 0.75. So 1.5 minus 0.75 gives us 1.5 MAS. Our new settings would be 65 kVp, 0.75 MAS. You notice here we have our contrast. Our long scale is going to have many shades of blacks and whites and grays in the middle. Short scale, which is bone, is going to usually just be black, white, and a little bit of gray shades periodically. Higher KVP is going to give us long scale, which will be better for organs and thorax and abdomen. Lower KVP is going to be better for our short scale or bone radiographs. Keeping in mind the tissue material density, from least dense will be air, then fat, water, muscle, bone, and metal will be the most dense. So what absorbs the most radiation would be gas, like air. What absorbs the least radiation, this would be bone. Scatter radiation is where we're going to have extra X-ray photons that bounce off of the interaction with nearby patient, table, or other objects. This will degrade the visibility, decrease our contrast, increase our density, make things darker when they don't need to be. So we don't want to harm our patient by having them get struck by additional scatter. Same thing with our staff and our film. So we want to decrease scatter whenever possible. And so what we'll do for that is to collimate. Collimate by closing our window. The other thing to think about here is the heel effect. The heel effect will have a stronger amount of radiation at the cathode side of the machine. So we position our patients accordingly. We need to restrict the beam by collimating. So we make our light source just enough to fit our patient and our marker. This will help to improve the quality of our image, reduce scatter, and reduce the excess exposure or excess density plus on our image. Artifacts are one last thing to think about. Artifacts such as the microchip, a D-ring on a collar or on a leash. These are things that can get into the way of our radiograph.